Um, okay, so I shall now discuss general properties of path integral. General properties of path integral. Let us first discuss Schrodinger wave function. So, so let's start with psi of if I'm using the same shortened if indicates x if tf. Okay, so that is by definition x if overlap with psi at tf. And then you can use the time evolution operator to write it as x if e to the power minus I by h bar times h tf minus ti psi ti. So I have expressed psi tf in terms of psi ti using this time evolution operator. And now you insert an identity, a completeness right here, to write it as x if e to the power minus I by h bar h tf minus ti xi psi ti integral of dxi. So initial position, xi is the initial position, and this is nothing but this object is nothing but the matrix element that we have been discussing. So it is integral dxi if I xi psi ti. So this you see okay, so let me write it as directly as psi I, where I refers to just like if, represents this if is a shorthand for x if tf, I is shorthand for xi ti. So that is the wave function here, psi of xi ti. So you see that so the final wave function can be written as initial wave function, but then evolved through using this propagator, right? So that is why it's called propagator. So you have some initial point event where there is a wave function here. So the wave function can be the wave function is a wave function with certain normalization property and so on. But then, so let me draw a cartoon here in order to explain. So it's like, so in the vertical direction, I have time in this picture. So initially, you had a wave function. Okay, so this is psi. So in this direction, this is the direction for x. So this is psi I, which means that at any particular time, well, of course, when I draw the wave function, it is about psi. I'm drawing this at a particular time slice, so that is ti. So that is the meaning of this picture. And then this extends along this x direction. So if you pick any point here, so that is a value of xi. Okay, xi is going from minus infinity to plus infinity. So you pick any point here, psi xi of ti, which is the value here. Okay, so suppose this is the psi xi ti. Every such point will evolve. Every such point will evolve in time and become a new wave function. And that wave function may look like something like this. Well, this is psi of f. Here also, this is the x direction, and it's a particular time, say tf. So what it means that pointwise, you have a particular value of xi, and you choose a particular value of xf. This evolution, that the wave function at this point will evolve into something like this at this point, at xf, tf xf. This information is being carried by that matrix element f overlap I. So it is like a propagator. So from every point here, so if in order to get a particular wave function here at tf it is receiving contribution from every point here. Okay, and those influences are being carried by the propagator. So this is fi, and therefore you could call them call that a propagator. Now you can show, so it's an exercise, it's an easy exercise. Show that I h bar del del t of say tf of fi, sometimes you call also, so let me give it sometimes, okay, so let me just introduce a new notation also. It's also called a kernel. It's called sometimes kf comma I. So k f is xftf, I is xiti. So these are two pairs of coordinates. Basically, those are events. So it is the same as this, and the exercise is to show that I h bar del del tf k f I is equal to the Hamiltonian with p replaced by minus I h bar del del xf comma xf k f I. Right? So hint is use Schrodinger equation for psi f. Right? This is your psi f, which is given in terms of psi I in this fashion. So this psi f satisfies Schrodinger equation, and so all the derivatives, the time derivative and space derivative acting on that, are finally going to act on this kernel or the propagator here. And so that is how you will be able to show this equation, this result. Now, a causal or retarded propagator is defined, so this is retarded, is defined by multiplying the original propagator with a theta function Tf minus Ti, where theta is the Heaviside step function it is given by theta x is 1 for x greater than 0 and 0 otherwise. Okay, so graphically, as you probably already know, this is x and this is theta x. For all x negative, it is 0. Okay, and for x 0 or greater than 0, it is 1. So this is 1. This is 0. That is the step function. Okay. Now you can write a representation. For this is theta x is the a representation of this is integral dy Dirac delta of y going from minus infinity to x. So this is the Dirac delta function, and you can easily check. So if this is the case, then it follows that the derivative of theta x is the delta function is equal to delta x. Okay, and you can check this result explicitly. So let us check it. So calculate dx minus infinity to plus infinity fx theta prime x. Since theta prime x is supposed to be delta x, we should get f of 0. The result should be f of 0. Okay, so let us check that. So what you can do is to write this as integral dx minus infinity to plus infinity del x fx theta x minus integral dx minus infinity to plus infinity f prime x times theta x. This result, since it's a total derivative, it goes to the boundary. So it becomes f infinity theta at infinity, which is 1, minus f minus infinity theta as minus infinity, which is 0. So the result is f of infinity minus, this is same as integral dx, since theta x is supported only between 0 and infinity. So from minus infinity to minus infinity to 0 contribution vanishes in this integral. So this is 0 to infinity and theta is 1. in that range. So this is also a total derivative, and therefore it should go to f infinity minus f0. So f infinity plus f0, and that is f0. That is what is expected. Okay, so what we will be using is this representation of theta of x, and as a result we have this equation relation theta prime is same as delta function. Now so with this understanding, let us now look at this retarded propagator, and let us calculate IH bar del del TF acting on this retarded propagator. Okay, so so for the original propagator, we know what the result was. It is IH bar del del TF acting on this propagator gives you Hamiltonian times the propagator. What is the difference if we consider, instead of the original propagator, the retarded propagator? What would be the difference? So that's what we are going to calculate, and the difference would come because now we have an extra theta function sitting in front. So let me calculate it here. So IH bar del del TF KR retarded propagator Fi must be equal to, okay, so IH bar when TF so recall that KR is nothing but this theta function times K. So when you take a derivative with respect to TF, it first acts on this and then acts on that. So there are two terms. So when it acts on this, it gives you a delta function. So that delta function is delta TF minus TI times K F comma I Fi. The second term is theta function, theta TF minus TI, and del del T of TF of K Fi. Now, so this is IH bar delta TF minus TI KF I, and this is IH bar del del TF IH bar del del TF of K, whose result we already know, and therefore that will be theta times H times K. So that is theta TF minus TI times H minus IH bar del del XF times K Fi. So final form is this theta F TF minus TI K Fi. But now this theta and K combined together gives you the retarded. So minus IH bar del del XF KR Fi. So basically with respect to the previous result, when we had taken the original propagator, with respect to that result, this result has the same term on the right hand side, but there is an extra term here. Now from the definition, see, this is delta function TF minus TI, So that would impose a coincidence of the time on this k. Now k being same as just a moment. So k, so the limit, so basically what we have is tf goes to ti of k if I, but k if I is nothing but this xf tf xf tf xi ti, and therefore in the tf going to ti limit, it must be it must go to delta xf minus xi. Right? So this must be given by, this must be replaced by delta xf minus xi. Now, so therefore the final result is that I h bar del del tf minus h at f, where the all these x's are calculated at xf, acting on the retarded, or maybe I should just get rid of this f index because it is not anymore. So let me write it as this: I h bar del del t minus h acting on the retarded propagator, where I take this to be xt xi ti. I got rid of the if subscript here, and that should be given by delta ih bar delta t minus ti and delta x minus xi. So this is why it is also called the kernel. So it's a Green's function. Therefore, it's a Green's function of Schrodinger equation. Okay, that's the result. So the retarded propagator is a Green's function of Schrodinger equation.